All right, party people, last class. Nobody's excited. We'll kind of quickly go through the stuff that we covered in terms of the chapters, and then you can answer any questions. So we did 1, 2, 3, 4. We skipped 5 because that was AC induction or synchronous machine motors. 6, a little bit of 7, and Appendix A, right? Those were sort of the chapters that we went through. Chapter 1 was sort of the fundamentals. What I mean by that is, how do we create a magnetic field? How do we get an induced force? How do we convert speed? How do we get torque? How do we get an applied force? All that stuff. It was a little bit, kind of a teeny tiny entry into magnetics, because pretty much when you're talking about a machines course, whether it's AC or DC machines, you always need magnetics. And so we needed just a little bit to be able to understand sort of the fundamentals. If you really want to get into magnetics, I think it's EET321 is I think the only undergrad class. Maybe there's one in physics too, because physics they have magnetics as well. So there's probably something in physics actually. But if you really want to get more into magnetics, you would take ECE351, which that talks a lot more about electromagnetics and electrostatics. So there's a bunch, there's electric fields and magnetic fields. But if you really want to understand the particulars of it, that's where it is. We don't need to get into the level of detail that they would in that class. All we need to know is that there is magnetic energy, how we get magnetic fields from current flowing through a wire, and how we can take advantage of that. And that was kind of the focus of Chapter 1. Chapter 2 was kind of a little bit of power, right? So this is when we talked about real power, reactive power, total power, power triangles. I guess that's probably about it, right? It really was the power chapter where we did all the stuff on what is the power, how do we get that. So we talked about power factor correction in Chapter 2. We talked about what is leading or lagging. Remember Eli the ice person? Current will either lead or lag the voltage. That's the key part of how we define power factor, okay? So you need to think about or focus on that. We always had S equals VI conjugate, and the reason why we need a conjugate is when you convert P of T, right? So P of T is the instantaneous power, and that's the real power that you have. But we do things in AC circuits land, we do things in steady state. So we have this real power that is being consumed or dissipated by the load, and then the reactive power is the one that goes out, sets up magnetic or electric fields, and then has to go back. It doesn't do any real work, okay? So that reactive power part is the part that we have to take into account. And when you multiply V of T times I of T and do all your trig identities, you end up with a VI magnitude times the cosine of the angular difference between theta V and theta I. That's the real part. Then the imaginary part was the negative VI sine of the difference in angle. And because of that negative is how we actually have to do the conjugate term. Okay? So your power triangles should always be in the opposite direction of your phasor diagrams. Your phasor diagrams are going to point down, right? So if voltage is my reference, my current points down, my S equals VI conjugate, my power triangle should point up. Chapter 3 was basically transformers. And we spent a lot of time going over transformers, how we have an ideal transformer as our starting discussion. So we had a loop of wire that carried current that was going around some sort of magnetic capable or magnetically conductive material that would have a flux flowing through it, and then the other side, if you will, or someplace else on the magnetic device, we would get an output winding, and that would be our secondary current, so we could extract energy. And the advantage of the transformer, most transformers, is we have electrical isolation between the two windings. They are electrically disconnected, which means that they are electrically isolated. So a fault occurring on one side does not affect the other side. All right? You can electrically isolate the two. We also talked about circuits. So magnetic circuits are very similar to electric circuits. We had an MMF, which was our voltage source, our flux, which was our current source, and our reluctance, which was our resistance, right? So all the circuit analysis or circuit stuff that you've developed in the past applies for magnetic circuits if you use those same concepts. If you have saturation, which is more common in way more common in magnetic circuits, you just have to be careful. Are you operating in some sort of saturated portion or unsaturated portion? So that's when we would use curves, right? We try to figure out curves where you're operating. That kind of lends back to chapter 1 a little bit. We also started to introduce, finally, some tests, right? No load and short circuit tests. And we were pretty consistent through almost all our machine study, where we did a no load and an open circuit test, or some version thereof, to be able to get the circuit parameters. And our circuit parameters were an R and an L and an ideal transformer, right? And then an R and an L on the secondary. We may have some magnetizing and some core losses. It just depends on how you have your circuit set up and how prescriptive you want it to be. Chapter 4 was, I'll just call it synchronous machines. So we started introducing the concept of a rotating MMF, right? So if we have a 3-phase set of currents flowing through a set of windings, we would get a constantly rotating magnetic field whose magnitude, that was at 1.5 times any individual magnetic field strength. And then we saw as we rotated through the AC sine wave, we would get a corresponding rotation of our magnetic field. If it was a 2-pole machine, you needed to go 360 mechanical degrees to have 360 electrical degrees. If it was a 4-pole machine, 180 mechanical degrees gives me 360 electrical. So we came up with that equation that your speed of operation is basically whatever the synchronous speed would be divided by the number of pole pairs, right? So 2-pole machine runs at 3,600 RPM, 4-pole machine 1,800 RPM, etc., etc., etc. If you remember from the lab that we did on Monday where we got the tour, they had one fairly sizable machine that I think was only, maybe it was 100 horsepower, and that was because its operating speed was something like 54 RPM or something like that. It was a pretty slow speed. It had a lot of torque, right? Because power, and this is one of those key equations from chapter 1, power equals torque times omega, right? So if you have a low speed and 100 horsepower, your torque has to be way up, right? So the shaft has to be larger, primarily because, or partially because, you're just moving a lot of torque, right? Think about if you're taking a bolt, that's a 1/4-inch diameter bolt, and you put a crack bar on it or a snack bar that you can easily snap it. Well, if you make that thing 2 inches in diameter and you put a lot of force on it, you would not be able, or you'd have a hard time breaking it off. So that's the concept of what they were doing there, okay? But the other reason why it was so big is you physically need room for more poles. You've got to generate a certain magnetic field. If you have 2 poles, you need room for 2 poles, 2 windings. If you need room for 200 poles, you physically need more space. So hydro facilities, the reasons why those are so big, it's not because the generators are big. I think the ones over in on the Stillwater that you drive by in College Ave, those are only about 3 megawatts apiece. Those are really small generators, but the size is partially because you spin at such a slow speed, you need so many poles to operate at synchronous speed. So synchronous machine has stationary field that is going to be connected to the AC supply, and a rotating field usually that is going to be connected to a DC field that you can vary. And the reason why you vary is because you either overexcite the machine or you under-excite the machine. It depends on the connected load. If you want it to be a leading or a lagging power factor, you either need to put more reactive power in to the to the machine, which means more DC field in. If you want to be able to take magnetic energy from the circuit or from the system you're connected to, you can put less magnetic energy in, meaning less DC field. Okay? And so that's eventually how you actually can control power factor on a synchronous machine that is connected to the grid. You just goose the excitation system up or down, and you can increase or decrease the power supply output. Okay? But the speed still needs to swing or spin at 60 hertz. If you're running isochronously, it means you're connected, to no other generators. You can run with whatever frequency your load or your system can handle. Right? Be careful, because stuff starts to work very differently when it's running at less than 60 hertz. That's why frequency on the grid is the most tightly controlled. If you see a 60.1 hertz waveform, that's very rare. It's usually like 60.01 deviation, so 100th of a hertz is the tolerance that they maintain. The voltage can go up or down. That doesn't have nearly the issue that frequency does. We also talked about the type of tests that we can do with a synchronous machine, which is essentially what? We did a not a blocked rotor, but a no load and short circuit test, right? And we did the no load and short circuit test at a specific value of field current so that we could compare apples to apples, because what we're trying to do is figure out that EA, right? We're trying to get that characteristic. And our equivalent circuit for a synchronous machine was very simple. It was a EA, it was a power supply in series with a couple of inductors and a resistor. Much simpler than the transformer circuit. And the reason why it was so much simpler is because the magnetic energy that you steal to set up or the DC field that you steal to set up the magnetic energy is completely part of a different circuit. So do you remember when you were taking semiconductor theory and you had two separate circuits, right? You were feeding into a BJT, and then that got shunted to ground, and then the other side was doing its own thing. You treated those as two separate entities, right? You analyzed one side of the circuit because it was grounded, and then on the other side we had the constant current source, or the voltage controlled or current controlled current source. You analyze the second side of that circuit completely independently. It's the same thing. These are two independent circuits. They are not connected to each other. So you can treat them separately, and that's why the synchronous machine circuit is much easier to analyze from the AC perspective. From the DC perspective, we oftentimes don't care because that's the DC field. We're not trying to figure out the impact of the system. That's a completely different ball of wax, so we don't worry about that. But we still did a very similar test to the no load and open circuit tests, right? We just did it at varying levels of field current because it sets up the magnetic energy different. And that was pretty much it for chapter 4. Chapter 6 was asynchronous or induction machines, right? And induction machines are the workhorse. If you were in the group that, and we talked a little bit about this on Tuesday, if you're in the group that I was in, AC electric, less and less DC motors, more and more induction motors. They are really the workhorse. You can do all kinds of speed control as long as you have a variable frequency supply. They work really well. Very efficient, no brushes, right? So all you have is 3 leads going into it, and that's it. You may have some stuff for monitoring, but it's very, very simple, very elegant machine. So the asynchronous machine is what we're going to be, most likely all of you. Question?
Yeah, the asynchronous machines, they had slip rings on them, right?
They can. Oftentimes they don't. So the only times you'll have slip rings and brushes on a synchronous machine is if it's a doubly fed like a wind turbine generator, or you're trying to add some rotor resistance. So if you remember that we did some MATLAB stuff where we just monkeyed with R2. So we saw how we didn't change the torque. We just moved the output torque. We just moved where that torque, that peak torque was generated or occurred at. So we just moved it up or down essentially. But yes, you do have access to it, but more often than not, you will not find it. Unless it's for generation, You very rarely find wound rotor type or doubly fed induction generators because they don't, you just put a variable frequency drive, it's cheaper. You just vary the frequency on the AC part and you get all the speed control you want. And drive prices have come way, way down. Anybody know why? In demand, part of it. Is the one key part of it too. What do you think an electric car is? When you put your foot on the gas, what do you think you're doing? Pardon? You're monkeying with the frequency essentially, right? To get more or less power out of the batteries and into your motors. So you've got variable frequency drives, driving down the road now. So the cost of semiconductor devices, the designs of them have simplified. I was watching a video the other day about, and it's actually worthwhile to do it. They took 6,000 hours to completely tear down a Tesla. So you can actually see how they make the batteries and all the power electronics. And you can actually look, they don't actually have circuit schematics. You basically just see a printed circuit board, but you can just see it's a variable frequency drive with a bunch of motors. That's all it is. Pretty simple, pretty basic design. But variable frequency drive prices continue to go down because, there's not 3 manufacturers anymore. Every car company can make them. Senior project, right? You can make a senior project and essentially do a variable frequency drive. All you have to do is change your oscillating frequency when you open and close, right? And you got it. So anybody hasn't got a senior project, I want to build a variable phase. How about single phase at first? We'll start off with single phase. The other sneaky thing too, a variable frequency drive is the easiest way to get 3-phase power. You can take single phase in and dump out 3-phase easily because the way that any frequency drive comes in, it's connected to 60 hertz. How do you get 30 hertz on the output? Well, you can do the rotating, the old school design, which is rotating. So you take the power off something that's spinning at a slower speed. In induction machines, right, we have an AC frequency that's different than our synchronous frequency. So we just steal off that and we can do it that way. But if you're going AC to AC without any rotating parts, there's only one way you can do it. Anybody want to guess? Pretty much anybody who has built a power supply, what's the first thing you do? You convert AC to DC. Yeah. So once you go AC to DC, you can switch back from DC to AC and you can go through 2-phase, 3-phase, a million phases. You can do whatever you want. But that's another advantage, right, with asynchronous machines. They don't have to run at synchronous speed. So starting up a asynchronous machine compared to a synchronous machine is a piece of cake. Flip the switch. As long as your system can handle the hit, right, because when we turn it on, there's a lot of load. Our slip, we based our concept on slip. So our slip was equal to 1 under locked rotor conditions or no load, or speed is 0, right? So at that point, we have a very low rotor impedance. So we have lots of current going into the machine. If you have an equivalent circuit, you just go ahead and build your equivalent circuit model and analyze it that way. That's what we did a lot in this class. I tried to be very consistent. I just did everything the same. All I did was, here's the circuit analysis. Let's do 2 loop equations and then write it in a matrix and solve for that. If you get problems like that on the test, that's what I would do. The only time you need to use those equations about the Thevenin stuff is if you're trying to figure out max torque. Because if you don't have MATLAB, if you have your calculator, the only way to do it is just trial and error, right? Did I get the peak value? Did I get the peak value? In MATLAB, we can write a for loop. Can you do for loops on your TIs? I would say those things can do just about anything, so I would imagine you could, but I don't actually know. I've never done it. So those are the only times you'd need those equations. What's the max torque? What's the starting torque? But in MATLAB, you can just write the basic equations. You don't even need to do that. Let's see, the asynchronous machine, we talked a little bit about service factors, right? Being able to run above nameplate. We looked at an actual nameplate. We looked at the KVA code, the insulation class, what temperatures those run at, all that type of stuff. We also said that the number of poles on the stator and the rotor have to be the same. Okay, so if you have a 4-pole machine on the rotor, you need a 4-pole machine on the stator. Yes, sir?
Well, we have to know the codes.
No. If you need it, I'll give that to you. That's just looking it up on on a table. That should be pretty easy. Okay? I think that was it for asyncs. And 7 is DC machines. So we didn't get too far into that because we kind of ran out of time. But DC machines are basically an AC machine that you just use a commutator to switch it around. If you remember, the output of a DC machine kind of looked like a sine wave, but a little bit cockeyed. Well, how do you get an AC machine? Instead of having things perfectly lined up, you skew the slots a little bit. So instead of those hard or harder corners, you just kind of tilt the machine so it smooths it out. So that they call that fractional pitch. So when you see how induction machines or synchronous machines are made, they use fractional pitch to do what? What happens when you have a waveform that should look like a sine wave but doesn't? What does it contain? Pardon? No. Noise, which is, what's another way to say noise? Sounds like a musical instrument, right? Anybody play guitar? Piano? What are notes? What's A and C and D? What's the difference between those two? Or three? It's one very simple thing. How does the A note differentiate from C? Frequency, right? That's all it is. It vibrates at a different frequency. And so a non-sinusoidal waveform has other frequencies in the waveform. Those are called harmonics, right? Multiples of the fundamental frequency. That's all they are. So you use 3/4 fractional pitch to get rid of your harmonics and smooth it out. So you don't need a filter system set up on a motor. You just actually build it in a way that sort of builds in sort of those filters for you. But a DC machine is basically, I want DC out, I want those sharp edges, so I'm just going to go ahead and build a machine that has no fractional pitch, and then I'll just skip it around and I'll get something close to DC. Not perfect, but close to DC. So if you could actually look at the output waveform of an older DC machine, it basically looks like a kind of a goofy sine wave that has been inverted. Remember we called rectifier? We discussed how we came up with the concept of a rectifier. It's based on the old terminology from DC machines. And Appendix A was really a review, but it was AC circuit analysis. Right? Single phase, three phase. What is an impedance? Where does the J term come from? Remember L di dt and C dV dt? You can come up with a plus or minus J's just from those equations. Right? The concept of X sub L and X sub C, that's all from that stuff. Yes, sir?
What's that say? AC?
Circuit analysis with an abbreviation or two. So we did a ton of AC circuit analysis. We also introduced the concept of a phasor diagram and an impedance diagram. Impedances should not show up on phasors. Phasors should not show up on impedances. Why? Because an impedance diagram is fixed. R and X do not change just because time has evolved. In a phasor, right, you're walking through the sine wave. So if you were to go look in time, the voltage that you see changes constantly. Where in an impedance, it's constant, right? It's just a resistor. It's just an inductor. It doesn't change. So understand the difference between a phasor diagram and an impedance diagram. And this sort of, the concept of a phasor diagram is super duper important, because as you start to get out in your careers, if you do anything with the utility industry at all, understanding phasors and how and what they mean really helps you out in the utility world, because you can tell a lot about an operation of a system just looking at a phasor diagram. If you remember Eli the Iceman, we drew a phasor diagram first to come up with a power triangle, right? So you can sanity check yourself hey, I've got this power factor. Does that make sense? Well, let me draw the phasor diagram. No, that really doesn't make sense. So you can do a lot of work with phasor diagrams and do that. We also looked at voltages, right? We could tell the output of a synchronous machine, whether it was a motor or a generator, just the angle delta. That angle delta, which is between EA and VT. Remember is this an impedance diagram or a phasor diagram? What's that? What is it? It's phasor because those are voltages, right? Those are sinusoidally varying constantly. This angle here tells me if it's a motor or a generator. The magnitude of this as compared to VT tells me if it's a reactive power load or reactive power source, right? Just by looking at the phasor diagrams of those. So those, you're trying to get some really quick understanding of stuff. Drawing phasor diagrams make things really, really useful. And then with three-phase, right, do we need 3? Do we need the square root of 3? A hint, the only time you really need to worry about square root of 3s or 3s is when you're dealing with phasors. If you've got a voltage phasor in there, right, you got to be mindful of whether I need 3 or square root of 3. If it's an impedance, it's always 3 if you're trying to go from single phase to 3-phase. Right? We live in a balanced world in this class, so everything is 3. In power, it varies a little bit because when I calculate S equals VI conjugate, if I want to go to 3-phase, now I got voltages and currents which are phasors, right? So I can't just say it's 3 or square root of 3, but the individual phases, right, you just have 3 times those. What monkeys it up is when I start throwing in those line voltages or phase voltages. That's when it gets a little more complexity into the equations. So you just have to be careful about that. So in half an hour, that's kind of a quick, I don't know if I gave you a jostling of memory stuff or... Pardon? Good. So I throw the floor to y'all. What are your questions?
Are you going to try and give us a question from each chapter? Or?
Except for DC machines. Mainly because we didn't really have any homework and we didn't have a lot of time. And as the tour of AC Electric sort of confirmed, DC machines are just going away. And if you remember when I said with the Prius, because it's really hard to find information about the manufacturers, the Prius uses a permanent magnet AC machine. Uses basically a machine, an AC machine that has a permanent magnet. So it's almost like a synchronous machine, but you don't have a separate field. It's all done by a permanent magnet. The Tesla uses an induction machine, a Tesla motor. I don't know of any vehicles that are pure, maybe they are purely electric like the Nissan Leaf or whatever, but the most popular hybrid car, right, which is a Prius, most people would say the Prius is probably the most widely accepted electric vehicle or partially electric vehicle, uses 3-phase AC machines. Nice smooth torque, nice way to go. DC machines, maybe like the Mars rover or something, where you have to have a limited amount of equipment to break down. So maybe that would be something where you wouldn't want to have a transfer of AC to DC or conversion from AC to DC to AC. But with semiconductor devices, I mean, semiconductor devices are pretty robust and reliable. They don't break all that often. It's not like mechanical stuff. I'm not looking at you just saying it's not like mechanical stuff rotates. I mean, it's just the nature of the beast. Mechanical stuff makes our life way better than electrical stuff, right? Mechanical stuff is that vibrating bed, right? That's mechanical. If you want to make an electric bed, I guess you could, but it would light up your life. It's just the electrical. The only reason why electrical engineers are really needed is what's the most efficient, best way to transfer energy. Yeah? Isn't electricity? Travels at the speed of light. Very efficient. Electric energy is the best. What are the other types? Thermal, right? I take something hot and I move the heat from one location to another. That is a transfer of energy. But how easy is it to move 1,000-degree steam from New York to Connecticut? Not too bad. How about New York to, I don't know, let's say Virginia? Pretty hard to do, right? And then you need a lot of mass to do it, right? You need some hot object that has expanded because of the temperature, where electricity, you just excite the electrons and they don't expand. They move faster, right? So electrical stuff is really where it's at because they are the key for moving stuff. If the future will really break free is once we figure out how to store electric energy effectively. We only have one device that stores electric energy. What is it? Pardon? No, battery does not store electric energy. Capacitors. Batteries are what a lot of people say. How does energy get stored in a battery? When you go buy a battery, what type of battery do you buy? AA, that's a size. Lead acid, nickel cadmium, lithium ion. Anything familiar about those names? They're chemicals, aren't they? No, they just basically, you take the electrons and you store, so you have lead plates, and then like a lead acid battery, you have the acid and you have the lead, and so you put, I think it's the electrons on the lead plates, and then the acid has all the positive, and until you complete the circuit, they don't travel all that well through the lead acid material. But they want to go between different plates, and so you just have the path. So either the negatives get stored on the plates or the negatives get stored in the acid. I don't know, but it's all done chemically.
So how does the battery electrons?
Well, so basically what you're doing is you're aligning things up, right? So when you have anything that is under a potential, you have the pluses and minuses lined up to a certain way. And so how you deplete that, you just let them become random again. So there's no voltage across it. You still have the lead and you still have the acid, and it's separate. You just don't have them aligned at that point. And it can store the charge because the lead and the acid don't conduct through each other. But right now it's basically the capacitor is the only one that legitimately stores electrons, right? You stick electrons on one side and then the positives are on the other side, and then you store energy. Now they're trying to figure out ultracapacitors, which, we think of a capacitor as two plates separated by the insulating medium, but the new ultracapacitors are almost like fingers. They're in 3 dimensions and they're, little outcroppings. They talk about nanotechnology. And so now they have much smaller capacitors that have, farad size. But to get a farad capacitor, that's a big, big capacitor. Huge. You might be able to find a farad capacitor for automotive applications. It's only running at 12 volts, so you can have very little separation, but it's the size of a 40, right? That's what I always say if it's a joke. Do they still make 40s? I was at the store the other day, now they have 25s, and I said, okay. I thought maybe they got rid of 40s. They still have them? What's that, James? Ah. Did you say I have a couple in my refrigerator or something, or? Oh.
Is anything flux related going to be on the
Not in a lot of detail. I mean, we might talk a little bit about how do you create a magnetic field from these, and so what's the rotating flux, or do we swap the fields around so you got to be able to use your fingers and whatnot? But that'd be the key part of it. We don't have to dig too much into that detail. Because most of us aren't going to be designing motors. We just have to understand how it works. And the big thing is speed. How do we get speed differences? The induction machine or the? Oh, the magnetic fields, yeah. You should look at the ECE351 book if you really want to get confused. It's all 3 dimensions. And the reason why EETs don't take a class like that is to really do magnetics. You really need to do vector calculus. You need to be able to integrate in 3 dimensions.
It counts as a math course for, like, if we were in math minor.
Oh, really? It does?
Math intensive, then you can get it to
Yeah. And the hard part is there are 3 coordinate systems to work with. So we live in Cartesian coordinate land, right? X, Y, and Z. Not in magnetics. There's cylindrical. So just imagine instead of 3 dimensions, X, Y, Z, everything is based on a cylinder. So you find your dimensions based on a cylinder. Then there's spherical, where it's not a cylinder, it's a sphere. It's basically a circle, 3-dimensional circle. And the reason why you have those different coordinate systems is, so if it's a square, a box, then you integrate with Cartesian coordinate systems. It's pretty easy. What about if it's a ball, a basketball? Well, it'd be easier to do spherical. What if it's a potato? Now you're starting to get a little more challenging, right? That used to be the famous one. How much energy does it take to bring a potato up to a certain degrees using magnetic field stuff? So that's why we don't do that. But yeah, it's a very math-intensive course. And that's one of those courses. I remember I took 2 EMAX courses, and it's, like, everybody ever been on a roller coaster? You ever been on a roller coaster and not strapped yourself in? You're just holding on to the railing, the handrail? Okay, so then you'd be fine passing ECE 351. I mean, I don't know if that's Aaron's experience or not, because you're just like, I don't know if I understand this material or not. I'm not sure how I'm going to get on the test. Yeah, I guess. I heard the current instructor, who's a really nice guy, he walks in for the first 20 minutes, he just fills the board up with material, and then he spends the rest of the class talking about it. So for the first 20 minutes, he just writes on the board and doesn't say anything. I don't know if that's true or not. What's that? That's accurate? Okay. And walks around the room. Like the front of the board's not enough.
Yeah, like there's this side. Like, so if this was like this symmetrical, he would start here and just go all the way over. And he like, and he really does it fast, so you have to write really fast and then he'll talk about it and you have to leave space so that when he talks about it, yeah, I just
Yeah. It really, I mean, once you get it though, like I got a little bit and pieces of it, it's really cool. It's like, whoa, that's cool. That's how that works. Like traveling waves and how cable TV works. I don't know if they used to talk about cable TV, now it's satellite. I don't know if they do. But, why do you terminate a coaxial line with a 300 ohm resistor or 75 ohm resistor? It's traveling waves. If you might YouTube it. I don't even know if they do that anymore. I don't have cable TV. I haven't had it for 15 years, so. Do they even have cable TV, or is it all just what do they call it? But I thought everybody just came in and wasn't coax. I thought it all came in through like Ethernet or. Oh, still is coax? Okay. I thought everything came in on Ethernet. That's how long it's been. Because all TV is digital now, right? So.
It's easy. I don't even have cable hooked up in my room because I just have like a Chromecast.
What's that?
Like it's just Google's like thing that you can just plug into a TV and then you can like pull out your computer or phone.
So you have a USB card, and everything comes in through
Any
USB?
TV with an HDMI.
It's HDMI.
Okay, HDMI. So you don't even use coax either. So.
Yeah.
It's wireless.
Yeah, with digital, I would imagine you might get traveling waves, but I don't know. So.
For the test, you just like what kind of sheet we're on.
I think we said 8.5 by 11, one full sheet,
Front and back.
front and back.
Yeah, I like it.
Just be careful, right? You actually went through and learned the material to put it onto a note card. That's how you learn the material. Anybody can be a copy paste person, Sierra. It becomes much harder when you have, when you just copy things over and then you're like, oh, I'm at a test and I just copied this down. I don't know what I copied.
So what do you recommend us doing for studying figure exams?
I'd look over the tests, make sure. Similar style questions, yeah. I'd look over the test, look over some of your homeworks. If you have time, You can watch there's 20, there'll be 27 classes today. You can watch 27, let's say each class was about an hour on average. It's 27 hours. If you do it at twice the speed, 13 hours, you're done. Just like that.
Yeah, but you also have to stop, write notes, and then you have to figure out what's actually useful and what's not useful.
Well, fortunately, you have 5 days to do it, so.
We had a lot of side conversations in this class, mostly about cars, which I did enjoy.
Well, cars, that's where the best technology is, right? Pardon? Yeah. For us, for AC machines, cars is where it's at, right? That's the big thing where we get to go. We could do motorcycles. They do have electric motorcycles now.
There's already one SPL.
And where?
So the project lab is motorcycle.
Oh, really? Wow. I didn't see that. When did it move in?
Oh, yes. Burning rubber on tiles.
It's in the senior project lab? Wow.
They cleaned it out yesterday.
Oh, yeah, it's been there for months. I don't know if it's
I know there was an electric car, but I didn't know there was an electric motorcycle. Other questions?
Will you be looking at your email between now and?
Yes. Yep. Absolutely.
What's your free time as well?
When's my free time? So I have class today at 2:30 to 4:20. So after this class, I have a little bit of time, and then I'll probably be here tomorrow most of the day. Monday, I think, do I have a final? Tuesday, I'll be here to kick off the final, but my wife's got a medical procedure that she needs a escort and a babysitter to. So it starts at 12:45, so I'll probably be here for the first little bit, and then Trey Pomerlo is going to finish proctoring it.
So everyone got $10. Give it a try.
He's pretty trustworthy.
When is our
It's Tuesday from 10:30 to 12:30 in this room. It should be on, if you go to Main Street, yeah. There should be a final exam schedule. Anything else? Do you have fun? Did you want to, now do you want to be a power person? Kyle's like, I don't know yet. That's where the jobs are at.
a lot of jobs doing other things too?
That's true.
Actually, you got a question that's kind of off topic. I got an email from the main. I'm trying to talk here.
Speaking of cars.
Main flagship careers. Do you know anything about that? Something about like RLCs, part of a flagship career place for Humane or something, and it's some sort of internship program that you can apply to. What was that?
Sounds like you should ask Cam. I don't know anything about it. Yeah, so if you want to poke fun at me, I'll be May 14th or 16th at the Westin in Portland. I don't have an official, I'm sort of one of the conference chairs, putting the conference together. So I'll be up there Monday morning kicking it off and then handling the panel session. Tuesday and Wednesday we have other people doing the panel sessions, but we'll be wandering around. I wrote the welcome letter. I helped write the, yeah, I knew that. I knew you were going, so. Well, I figured he didn't say your name, but he said somebody from EET who's got a new student. It's not a hard guess. It wasn't going to be Dylan, so.
Yeah, I asked Dylan if he's going, but he went. He's going to be in Mexico anyway, but he went not last year, maybe last year. I can't remember.
We're losing control. So, what other stuff? But Kyle's absolutely right. There are lots of other jobs, but this industry, there's a tremendous demand, and it's going to only increase.
Yeah, so that means there's less effort for us.
No, there'll be more effort on you, because if there's more demand, it means there are less people, and they still have to get the same amount of work done, so they just keep pushing more work on you. And the only way they keep you from leaving is they push higher salaries. So starting salaries next year, I would imagine, are going to be, if not 70, darn close to starting $70,000 a year. Which is great, yeah. I mean, that's pretty sweet.
My parents are really sad.
Why?
Well, that just if I end up graduating and then making
Well, I bet you secretively though, because I'm a parent, you always want your kids to do better than you. So you might tease them a little bit and saying, well, that's not fair, you're making more than me.
Yeah, oh, no, they're definitely happy.
Yeah.
Because, yeah.
I'd be happy too. It's like, hey, son, can I borrow some money? Can I retire? You know how much you've cost me? You got a lot to pay back.
They've helped me out plenty. So
I say any parent will, you know, who's done a reasonably good job, which I'm assuming you're in college and your parents have done a reasonably good job. You know, they put a pretty big commitment to you. Speaking as a parent of 2 kids, it's the stuff you need to do to keep them happy and healthy is you better be willing to sacrifice a lot. It's more than a second job. It's a job without sleep. And no personal time or personal space. Yeah, I mean, they're usually it's good, but there are parts when your kid is sick and you know you have to do things that you're like, why am I doing this? And you know, my son is potty trained, but he doesn't know how to clean himself properly, and so whenever he's done going to the bathroom, it's like, Papa, Mama. I mean, you just do it, you know. And at first it creeps you out, but after a while you just don't even think about it. You just say, you just do it, and you say, I'll just go wash my hands. I'm assuming none of you have kids, or if you do. Oh. So you know what I'm talking about a little bit.
I have a young dog.
You have a young dog?
Yeah.
Picking up poop there are some similarities, especially when they've eaten some bad stuff. You got to spend a lot of time cleaning it out. But yeah, it's different.
Yeah.
Anything else? No more questions? All right, I need a volunteer because I've got ABET evaluations. These are just about the class, and these are essential for you more than me. I mean, they are important to me, but if you ever want to become a PE, then your best bet is to graduate from an ABET accredited institution. We are ABET accredited, and it makes your life a lot easier. If you do not have an ABET accreditation, I'll shut the video off because nobody cares about this. If you do not have ABET accreditation, good luck